and this is my physics lab for oscillations presentation. So the goals of this lab was to understand oscillating motion of spring mass. To do that, we compared the predicted motion and observed motion of a mass attached to a spring. To compute the energy change, we used the Python code and showed the kinetic energy, gravitational potential energy, and spring potential energy, along with the total energy. So some results. Both predicted and observed motion graphs are very similar, and the change in total energy of the system is 0 at every interval. At the top right, you can see the tracker image. So some important formulas are F net equals change in momentum over change in time. Momentum is mass times velocity. Velocity is change in position over change in time. The change in energy of the system is work of the surroundings plus the heat. F net is the force of gravity plus the force of spring. Potential energy of gravity is mass times the gravitational constant times change in y. K, the kinetic energy, is 1/2 mv squared. Spring energy is 1/2 ks squared, and then to solve for s, you do L minus L naught. The observed conditions, so the system is the earth and the spring and the mass. There's nothing in the surroundings. Delta E of the system is 0. Initial position is negative 0.111, negative 0.6550. We start at 0.4575 seconds. The mass of the object is 0.402. It ends at 9.7972. The time intervals is 0.095. On the right, you can see our free body diagram where it just has spring and gravity on the ball. So here are code initial conditions. You see everything pretty much had on the last slide. And over here we have 9.8 as the gravitational constant for Earth. 6.872 is calculated for the spring constant, and then the relaxed length of the spring we found was 0.162 or 0.1261. So this is the rest of our code. As you can see in the top left, we found the spring. As you go down, you see the end time. Calculated the gravitational force, the spring force, the net force. We used the momentum principle to update the velocity and position. We updated the spring using all the formulas. On the right, we calculated the change in energies using the formulas we gave on the formula sheet. We calculated energy changes. We plotted the position, and yeah. So this is our code results. This top is the X. You can see the X and the Y look pretty similar. They're the X and the Y versus time. And the right is like the final graph. So you can see potential gravity and potential spring cancel each other out pretty much. Delta E is always 0, and then blue oscillates over the 0 mark. We compare the model versus computational, and as we said in the first couple slides, they're very similar. X is a little bit more accurate than the Y though. Discussion. So is the change in we're talking about the change in energy versus the time graph. The change in gravitational and spring potential energy are opposite signs, and they oscillate. So as the spring potential energy increases, gravitational decreases. The change in kinetic energy also oscillates to offset the potential energies, and it's slightly less than all the other energies. Potential versus the time graph. The X position graph is accurate while the Y position graph is not as accurate. What does it mean? Is the energy principle satisfied? Yes. Using the change in energy versus change in time graph, the sum of the change in the kinetic energy, change in gravitational potential energy, and the change in spring potential energy, the total energy equals 0. This is because gravitation and spring cancel, and kinetic has less magnitude than the total potential energy. So what does it mean? Oscillation period based on the X and Y positions, the time between the crest or troughs and the time to complete one cycle. The average oscillation period can be found by dividing the sum of the 3 by 3. We found the average oscillation period of X is 0.1646 and Y is 0.1489. That difference can impact the values of the constant K spring force, and it's likely caused by tracker error or unknown drag. So some possible error is code input errors, tracker marking error, human error, not accounting for drag, or not accounting for other energies. And yeah, that's it. Thanks for watching.